Good morning, afternoon, evening, TCAP Bio. Welcome to our fourth installment for Domain 1. Again, I'm back to Eminem because I ran out of Pearl Jam. So, let's go ahead and just want to play for this one. Little Eminem against Survival Fittest. So, this quick one is going to be evidence evolution. This is only about 10 slides. And some of this should be review from Bio, but there's some things that they like to have on the AP exam in terms of evidence. So first one is be geological evidence. So we've got radiometric dating. So we use the date of geological formations and fossils to help give us an estimate of time. It establishes a chronological history of the Earth and establishes the Earth's age at about 4.5 billion years. So that's the first type of evidence. The fossil record, let me move this over so we can see that. I believe that is a trilobite. Also establishes history of life on Earth because we can, specifically if you find like Darwin did when he was in the Andes, high up in the mountains, he found remnants of aquatic fossils. So that would indicate to him that at some point, those mountains, due to mountain formation, had pushed up, and were at one time at the bottom of the ocean. Also, living organisms resemble fossil forms. So if we look at modern day animals, we tend to find organisms that look kind of like them in the fossil record. I think this is an armadillo, an ancient armadillo, and if you compared it to modern day, it has some similarities. Transitional fossils, Tiktaalik, they show evolutionary progression between groups. And so this one's famous. There's a book by, called Your Inner Fish, and it talks about Tiktaalik. And if you kind of look at this transitional fossil of how maybe the transition from land to water, or water to land. Sorry, it's early. It's like 7 a.m. here in Tiffin's beautiful south side. Anatomical evidence. And so similarities and differences in anatomy, or what's also called morphology. So we have these things called vestigial structures, and these are structures that have lost their primary adaptive purpose. So for example, in a whale, they do have hind limbs, even though they don't swim. Even though they do swim, they don't walk on land. Snakes will have a vestigial structure, looks like a pelvic bone. So this would also indicate a common ancestor, and also change over time and evidence for evolution, because these structures were present in a common ancestor at one point, and over time, these structures, since they were no longer needed, the environment selected for them to not be needed, and so they eventually became smaller or not used. Homologous structures, though, these are structures that are present in a common ancestor which has diverged. So divergent evolution is if you branch out this way. And so vertebrate limbs, the key there is vertebrate. So all of these organisms are vertebrates that have a spinal or back, vertebral column, backbone. And so if you look at the limb of a bat, a dolphin, and things like us, you'll notice that 5 phalanges, right? Similar phalanges, similar bones in the carpus or in the carpals. And so that would indicate a common ancestor. Analogous, these they have evolved multiple times in different lineages to fill similar adaptive needs. So flight, right? Wings are analogous. If you compare the wing of a bird to the wing of a butterfly or a moth, the wing of the bird has bone, is bone and feather, where the wing of a butterfly does not have bone. It has chitin, whereas the bird is a vertebrate, the butterfly is an invertebrate. So when we talk about homologous structures, similar structure, maybe a slightly different function. Analogous structure, similar function, definitely different structure. Chemical evidence, I don't think I need to go over this again. But one thing that we can do is compare DNA of species. The more differences they have, the more likely they diverge at some point. So DNA, again, to RNA to protein is your central dogma. And then also our chemical evidence, our DNA and RNA, has also been used to establish the evolutionary relateness or phylogeny of all living things. And so we look at here, this is a phylogenetic tree, which we're going to talk about in a later session. And these phylogenetic trees, you can see what's in red: protozoa, alga, plants, slime molds, animals, fungi, eukaryotes. Everything that's in green and blue are prokaryotes. But as you can see, the gram-positives up there, so those are all the way down to the proteobacteria, prokaryotic. They have a similar evolutionary relationship. And the thing right here in the middle, that would be the common ancestor of all things on Earth. And so another way that we can test evolution or create evidence for it is by doing some mathematical modeling, which we're going to talk about. I'm going to do a whole section just on that. Computational analysis, the ability to take large amounts of chemical data and you run it through a computer, and that can establish evolutionary relationships among organisms. And so by looking at how many sequences they have alike or how many are different, which they like to often ask, but also Hardy-Weinberg theory, which is the mathematical part, the ability to quantify the amount of evolutionary changes from generation to generation. So this is actually a way that we can look at some data, we can look at some math, but we can look at ways to see how things are related. So when we look at evidence of evolution, we can also look at evidence of common ancestry. I'm just going to throw this one in with it. And so the universal genetic code, this is often a multiple choice question. This is always your go-to. If you've got similar DNA, would indicate that would be evidence of common ancestry. Common metabolic pathways, so glycolysis, which is literally the breakdown of glucose, this would be also an example of common ancestry because glycolysis is present in all living things on Earth, everything from a simple prokaryote all the way to complex eukaryotes. Cellular morphology, again, these pictures are not to scale, but if you look at a prokaryote and a eukaryote, they have some similar things, cell membranes, right? They have genetic material, and ribosomes. So ribosomes are key. Now the ribosomes are slightly different in each, but that would indicate a common ancestry. And then my favorite, endosymbiosis, which we'll talk about more in a later domain. This is the idea that a free prokaryote was engulfed by a eukaryote. I gotta turn the lights on, sorry. I really don't know how I'm gonna ever fix that. But the idea that an ancient prokaryote was engulfed by an ancient eukaryote-like organism, they formed a relationship, and that's how we have our organelles. We'll talk more about that in domain 2. So that's it. We're going to do math skills in the next one. So I hope this one's only about 7 minutes. Again, hopefully we're face-to-face and I can do this. You just have to do these for review. So again, this is me. It's signing off from room 102 in the heart of Tiffin Columbian. I don't know if I can get the music to play. Oh, there we go. It's a little early coming in. It's like 7:06, but all right. Sign off. Have a good one.